Hello class, these are our notes for section 5.2 for calculus. It's the natural logarithmic function. Today we're looking at integration. So section 5.1 was taking derivatives. So what we learned, I'm just going to do a quick remember from our last lesson. If y is equal to the natural log of x, then y prime, our derivative, is equal to 1 over x. If y is equal to the natural log of u, where u is some kind of function, and then I take a derivative with respect to x, y is going to equal u prime over u. So I always like to go through like why we have this u prime over u, and I want to remind you about that as well. So that's basically what it's just saying is chain rule. So if I had a function like y equals the natural log of x squared, and I just took the derivative and used chain rule, I would say, well, y prime is 1 divided by x squared times, and then I would do my derivative of the inside function of the x squared. So derivative of x squared is 2x. And then I would have to multiply those together, and y prime would be 2x divided by x squared, and then I go through and reduce. But basically what I end up with, right, is I end up with my original function, my u, and my denominator, and then my numerator is u prime. So knowing that kind of chain rule step, y, oh, I forgot about my prime on this one, that if y is the natural log of a function, y prime is u prime over u, just saves us from having to do all that multiplying and stuff. So it makes it a little bit easier. So this is just the second one up here. Y equals natural log of x, y prime 1 over x is just my normal natural log. The second one is like the chain rule version. So let's go ahead and erase this and get it out of the way. So today we're looking though at, I always talk about how we're working backwards when we're integrating. Our brains really like taking derivatives. They're easy, we just follow the steps. But when we do integrals, it's a little bit trickier. So let's think about how, if I have the integral of 1 over x dx, well, looking at my rules over here, that's just going to be the natural log of x. But I want to think about why it works that way. So we've done a bunch of stuff with power rule, and I feel like there's some of you that are thinking, well, this is just x to the negative first power. It's just an exponent. All I'd have to do is add 1 to my exponent. So negative 1 plus 1 is 0, and I would divide by that new power. And as soon as I write that out, hopefully you can see why it doesn't work. So that's why we can integrate lots of different exponents, but not negative 1. And that's because it's not even a power rule. It ends up being this natural log instead. So this is going to equal the natural log of, and then I want to add in the absolute value of x plus c. And that's because I can only take the log of positive things. So when I'm working backwards, I have to make sure that I allow for that and say like, hey, x has to be positive. If I have the integral of u prime over u, and remember u prime like is my du, I don't have to write a dx or anything with that. When I integrate that, I'm going to have natural log of the absolute value of u plus c. So we're going to go ahead and try using this now. So my first one, very classic, right? I can see 2 over x, so I would just write the 2 in front of my integral. And then I have 1 over x dx. And then that looks exactly like this natural log when I integrate. So 2 times natural log of the absolute value of x plus c. And then if I wanted to be fancy, I could remember my log rules. And I could say, well, if I have a coefficient of 2, really I could make that an exponent. So I could write it as the natural log of x squared. And then when I write it as x squared, I don't have to worry about forcing it to be positive anymore, because when I square it, it will be positive. And I could write plus c. So I think different problems are going to require different ways of writing it. We need to know that they're equivalent. When you're checking your answers, it might look like the first answer, it might look like the second answer. So that's up to you to recognize that they are equivalent. And like I said, I don't know that there's a best way to write it. It depends on what we're doing. So on the next one, I can see that I have a more complicated looking denominator. So here I'm thinking about that integrating u prime over u. So if my u is my denominator for x minus 1, let's think about what our du is. Well, our derivative of 4x minus 1 would be 4 dx. And I don't have a 4 here. So I'm going to go ahead and rewrite this and make this 4 over 4x minus 1 dx. So then I have a u prime over u. I have my derivative on top of my denominator. And then because I multiplied by 4, I also need to multiply by a 1/4. I'm going to put that in front. So then we end up with 1/4 times the natural log of the absolute value of 4x minus 1 plus c. And again, you could make it a fourth root. The squared one was kind of nice. It kept us from having to write the absolute values. It looks pretty simple. I don't know that a fourth root is going to make this one look more simple, so I'd probably leave it. So a lot of times that's how I make the decision, is just what I think looks prettier. But once we start actually solving some problems, we will make decisions based on a better matrix there. So this one, we're looking for the area of a region. So remember, when we think of area, we have to make sure that we look at a graph and know if our region is below the x-axis, above it, what's going on. And this is my function, y equals x over x squared plus 1, the x-axis, and the line x equals 3. So if we just do a quick graph on this, you could use a graphing calculator, you could use Desmos, we come up with something kind of like this. So it looks kind of like a square root, but maybe a little bit curvier. The scale that I'm looking at, I have 1/2 here. 3 is kind of out in here. So all of it is above my x-axis. And I don't have to worry about a bound on the left because it's bounded kind of naturally here at the origin. So if I'm looking for this area, what I'm really trying to find, my area is going to be the integral from 0 to 3 of my function x over x squared plus 1 dx. So I know that I have a bigger power in the denominator. So this looks like a u prime over u situation again. So if my u is an x squared plus 1, my derivative of u, my du, is going to equal 2x dx. So I would need to multiply by a 2. So I also need to multiply by a 1/2. So I'm going to write equals 1/2 times the integral from 0 to 3 of 2x over x squared plus 1 dx. And I could even write the dx in the numerator, right? It doesn't matter. So now I have this all set up. It's going to be the natural log of the denominator of my x squared plus 1, because this is u prime over u. So that's going to integrate to, if I have this, right, it's going to integrate to natural log u. So that's what I'm doing. I'm going to have 1/2 times my natural log of the absolute value of x squared plus 1. And I don't think we have to have absolute value signs there, do we? Because x squared plus 1 is always going to be a positive. That's not a concern. So I'm going to change the way this looks. I'm going to write 1/2 natural log x squared plus 1. And then we want to evaluate that from 0 to 3. So I think I'm going to evaluate and then multiply by the 1/2. So this is going to be 1/2 times the natural log of 3 squared plus 1. So 3 squared plus 1 minus, and I said 1/2 and I randomly wrote out a third, minus the natural log of 0 plus 1. And then kind of moving right along here. So 1/2 the natural log of 10 minus natural log of 1. So I know that the natural log of 1 is just going to be 0. So this is a 0. Remember, e to the 0 power equals 1. Anything to the 0 power equals 1. So this is just going to be 1/2 the natural log of 10, or the natural log of the square root of 10. Either of those would be good answers. All right, we've got a bunch here, and I think you can see really clearly, this is where I would probably have you work alone for a little bit in class, that if you think about it, like my denominator is x cubed plus x. And then when I take a derivative, oh, look, that's going to be 3x squared plus 1. So this is clearly a u prime over u situation. So because I have u prime over u, it's just going to integrate and be the natural log of, I do need absolute values here, x cubed plus x, and then plus c. Let's see if we get lucky like that on the next one. So on the next one, if my function is tangent x, the derivative, the u prime, would be secant squared x. So this one works out as well. It's just going to be natural log of the tangent of x plus c. Let's see, on the next one, doesn't work out quite as well. If my u is x squared plus 2x, my du, my derivative of x squared plus 2x, would be 2x plus 2. But what I do notice is that is double the x plus 1, right? That's if I take my numerator and I multiply it by 2. So I'm going to go ahead and do that, make this a 2x plus 2, which means I've essentially just distributed a 2 into both of them. But if I multiply by 2, I also have to multiply by a 1/2. And then my denominator is x squared plus 2x dx. So this is going to be 1/2 times the natural log of x squared plus 2x plus c. Let's look at our last one. This last one, if my u is 3x plus 2, my derivative of u, my du, would be 3 dx. So I would need to have a 3 in here, and then also a 1/3. So now I have u prime over u. So 1/3 of the natural log of the absolute value of 3x plus 2 plus c. So this is just to get us a taste of how these work, to do a bunch of easy ones, kind of one after another. And they got a little bit tricky at the end where we had to multiply by a number, but they weren't that hard. So the next couple we're going to look at like what happens when math gets a little more challenging. So on 5, what I notice is that, well, this is a mess, right? I have the same degree on the top and bottom. So on the numerator, I don't just have the derivative of the denominator. It's not a u prime over u, at least not yet, right? It doesn't look like that. So it really seems, though, to me, if you look at the numerator, x squared plus x plus 1 over x squared plus 1, like my numerator is bigger than my denominator. So one way to handle this, and this is maybe not the easiest way, I'll show you kind of a cool trick in a second, but one way to handle this is to take the numerator and divide by the denominator. So essentially do some long division. So x squared plus 1 divides into x squared plus x plus 1 one time. And then we'll multiply it back and write it underneath. And then remember, we always subtract everything. So x squared minus x squared is 0, 1 minus 1 is 0, but we have to bring down our x. And then x squared plus 1 is too big to divide into x. So basically my answer is 1, right? But I have a remainder of x over x squared plus 1. And then what I can do is I can just go ahead and integrate this. I can make this a 1 plus x over x squared plus 1 dx. And if I split this into two integrals, the second one, when I'm looking at this x over x squared plus 1, now that fits like our u prime over u. So there's another really slick way we can approach this problem. The other way that we can approach it is we can say, like, this is kind of cool. My numerator has an x squared and a 1, and that's my denominator. And so instead I could rewrite this, and I could make it x squared plus 1 plus x over x squared plus 1. And remember, we can break apart the top of a fraction if we keep the denominator. So then I could write this as the integral of x squared plus 1 over x squared plus 1 plus, and then my other part of this would be x over x squared plus 1. And I guess at this point I should really have like some big brackets over this entire thing and put a dx out here. And then, because my first fraction is x squared plus 1 on the top and bottom, that's just going to be a 1. My second fraction, I have the x over x squared plus 1, and then don't forget the dx. So at this point, it doesn't matter which method I use. I do need to split this into two integrals. You probably wouldn't have to. It's up to you. But I think for students, especially learning this, it really helps to split this up. And on my second integral, x squared plus 1, I was thinking dx and writing 1 at the same time. On my second integral, I want to make sure it's set up for that u prime over u integration. So if my denominator, my u, is in x squared plus 1, then my derivative of u, my du, would be a 2x. So I would need to have a 2 here and also a 1/2. So now I'm all set up to integrate. So when I integrate 1 dx, that's just x. When I integrate my second integral, I'm going to have 1/2 times the natural log of the quantity x squared plus 1, which will be a positive. If I square something, that's positive. If I add something to it, it's positive. And then plus c. So in this chapter, we're going to get a lot of these kind of weird answers where we've got natural logs mixed with other things. So it's going to be kind of interesting. So for example 6, we're going to, there's a couple different ways to do this one, but we're going to use one that kind of takes advantage of a technique we haven't done in a while. So I can kind of see this is going to have to be some kind of a u substitution, right? I can see I have an x plus 1, that's like an inside function being squared in my denominator. So it's really tempting and it makes sense to just say, well, u equals x plus 1. But then my derivative of u would just be dx, right? It would be a derivative of x is 1, so I just have a dx. And that doesn't really help me. So what I end up with here is I end up with 2x over u squared, and then I have a du. So I still have this 2x I have to worry about. So the trick that we're going to use is we can actually take our u substitution, u equals x plus 1, and we can solve that for x. So if I solve that for x, I am subtracting 1 on both sides so that u minus 1 is equal to x. So now I have a substitution that I could use for x as well. So this isn't something that we use all the time, but it's really cool when it works out. So 2 times the quantity u minus 1. And then I have u squared, and then I have du. So I'm just going to go ahead and leave the 2 in the front. And then I have u minus 1 over u squared. And then let's think about how I could separate this out into 2 fractions. So I would have u over u squared minus 1 over u squared du. My first fraction can be simplified into just being 1 over u. And then the second one I'm going to write as u to the negative 2 power. Okay, so now we're ready to integrate. So when I integrate, when I'm integrating 1 over u, that's just going to be my natural log. So I'm going to have 2 times the natural log of u minus, and then this one's also going to have a 2. I'm going to go and distribute that now, right? The 2 has to go to both of them. My second one, I want to increase my power to negative 1 and then divide by negative 1, and then we have a plus c. So let's go ahead and clean up a little bit here. I'm not going to put u back in yet. I'm going to rewrite this as 2 times the natural log of u plus 2 over u plus c. And then I would want to actually substitute u back in. So when we do that, we're going to have 2 times the natural log of x plus 1, and this should be absolute value, plus 2 over x plus 1 plus c. And then the last thing that I could do here is I could even make the 2 into an exponent. So I have 2 times the quantity x plus 1 squared plus 2 over x plus 1 plus c. There we are. Next is asking us to solve the differential equation. So remember, that's like we have dy, right? And we have dy, we want to integrate dy to come up with y. That's what they're meaning. They're meaning like find the y equals. So we want to integrate. So first we want to, I got a big jumbo eraser today. First we want to multiply both sides essentially by dx so that we have dy equals 1 over x times the natural log of x dx. And then there's something about that natural log and that 1 over x. So what I'm going to do, I'm definitely integrating both sides, right? So that would be my next step. But then I feel like I want to show this being multiplied like 2 different fractions. So the left-hand side is now y. I'm going to write this as 1 over natural log x times 1 over x dx. So if I think about now what's going on, when I think about 1 over x here, I think of how that's the derivative of the natural log. So if I think about a u substitution here where u is the natural log of x, well, our derivative of that, our derivative of natural log is going to be 1 over x dx. So if I look at this, like this is my du, all of this stuff together, and this is really essentially 1 over u. So let's go ahead and actually write that in, and then we're going to integrate. At this point, a lot of times I'll just kind of look at these notes I've made and I won't actually switch to u. I don't care either way. Like if I see 1 over u, oh, I know all I have to do is now change it to natural log of u. But maybe it actually helps you to do the full, like, rewrite it this way. So when we integrate, it's going to be natural log of absolute value of u plus c, which means natural log of, well, u is a natural log of x, so absolute value of natural log x, and then plus c. So it's kind of cool. We end up with a natural log inside a natural log here. The next couple, we're going to look at integrating trig. So we know integrating sine and cosine are really easy, right? If I'm trying to integrate cosine x, well, I know if I start out with sine and I take the derivative, it's just cosine, right? So that's going to just be sine x plus c. It's really easy when we try to integrate just sine x. So we know if we start with cosine and take a derivative, it's negative sine x. So this one is going to switch signs, but those are easy. But if we look at tangent x, we don't have a simple integral for that, right? If I start out with like y equals secant x, and I take my derivative, it's secant x tangent x. If I start out with tangent x and I take a derivative, well, that's going to be secant squared x, or secant of x and then squared. So this is just a single factor of tangent. So it's really weird. So we can use natural logs now to do a lot of integrals that we couldn't before. So I'm going to rewrite tangent, and I'm going to rewrite it using sine and cosine. So tangent is going to be sine x over cosine x dx. And now if I think about how u is my cosine x, so if I started out with cosine x and I take a derivative, I get negative sine x dx. So this is really another one of those u prime over u situations. So I do need to add in some negatives, right? So let's go ahead and make this a negative sine x. And then we need to multiply by a negative in front as well, because two negatives multiplied really make it positive. We haven't changed anything. But now I just integrate with that u substitution. So now I'd have negative of natural log cosine x. Make sure you have your absolute value signs, plus c. So again, it allows us to take an integral that we couldn't before. And it's kind of unexpected, right? We wouldn't expect to integrate tangent to integrate trig and get a natural log. So it's really cool to me how these natural logs kind of pop up all over the place with power rule, with trig. All right, so let's look at our last problem. So for the last one, we're looking at integrating secant x. So we're going to do something entirely unexpected, and we are going to multiply. We're going to pretend we have secant x over 1, right? Like there's a fraction, and we're going to multiply it by secant x plus tangent x over secant x plus tangent x, which is just wild. You would never say like, hey, I want to multiply by this giant fraction. So when we multiply that, our numerator is going to have secant squared x plus secant x tangent x. And you might be recognizing some trig now and thinking about patterns. Our denominator is just going to be secant x plus tangent x. So remember, just on our paper up above here, we wrote that the derivative of secant is secant x tangent x. So here's my secant. And the derivative of that is this guy right here. And then if I look at tangent x, so tangent x is right here, my derivative of tangent x is going to be secant squared x. So I really have that u prime over u again. So if I let u be my denominator, if I let u equal secant x plus tangent x. Well, my derivative of that is just going to be secant x tangent x plus secant squared x, which is the numerator, but just in a different form, right? Just flipped around. So all I end up having here is the natural log of my denominator, secant x plus tangent x. Don't forget your absolute value signs, and then plus c. So it's really cool how this works out. So at the bottom of the page here, there's integrals for 6 trig functions. As always, like there's some we use more than others. You definitely want to have tangent memorized. I feel like secant's a little more common. Cosecant we don't use as often, but the tricks that we used for tangent, you could use a similar trick to do cotangent. So I feel like if you kind of memorize that trick, you could do both. And then our trick for secant, you can use for cosecant as well. So we do have more memorizing to do. And there's a little note here at the bottom. It says by the end of section 5.7, we will have 20 basic integration formulas to have memorized. So we really want to have them memorized as we go through. If you have to, write them on flashcards or something, but it's really going to slow you down if you're having to look up integrals constantly. All right, class, as always, if you have questions, don't forget to ask.